This is the lecture for Monday, April 15th. Today we'll be talking about the quark gluon plasma, and these slides were produced by John Harris at Yale University for some summer school lectures that he gave a few years ago. Okay, let's first talk about the main heavy ion collision experiments that probe the quark gluon plasma. So first, we'll talk about the relativistic heavy ion collider, which is at Brookhaven. And so you see some of the detectors and the corresponding collaborations. And so for RHIC, the corresponding energy for each pair of nucleons colliding, so the proton-neutron pair collision, the energy is about from 5 to 200 gigaelectron volts. Now, by comparison, the experiments at the LHC, the Large Hadron Collider, for their heavy ion collisions, they have ALICE is the main collaboration that does the heavy ion collisions, although some of the other collaborations are also looking at heavy ions, but ALICE is designed to look at heavy ion collisions. And for each pair of nucleons, the corresponding energies is about 2.7 or so TeV. This is tera electron volts, as opposed to gigas, another factor of 1,000. And after the upgrade in 2015, went up to 5.5 tera electron volts, and this should increase further with further upgrades. Okay, so they're investigating the properties of hot QCD matter at between 150 megaelectron volts in temperature to about 1,000 megaelectron volts. Okay, here's just some interesting facts about the top physics newsmakers of the decade from 2000 to 2010, as compiled by the American Physical Society. So there was the Large Hadron Collider. That's not a real surprise. The discovery of the Higgs boson, as well as some of the heavy ion results that we'll talk about. And you can see some of the other exciting things that went on. So that there was the discovery of these pure graphene sheets, carbon nanotubes, and then there's these negative index refraction materials that give you these cloaks of invisibility, where you can make light bend around objects and make them look apparently invisible. And then there's the Wilkinson microwave anisotropy probe to see the signature of the Big Bang. Then there's quantum teleportation, where you can actually transport information across large distances. So in other words, make copies of a quantum state that exists here, but you can imprint that information at some other place. And then there's a quark gluon plasma, which we'll talk about today, which tell you the conditions of the early universe, how the hot quarks and gluons are behaving. And then there's also this gravity probe B, which observe the basically the frame dragging effect in general relativity. There's also these optical molasses experiments where they slow down light and actually it's pretty impressive that they can slow down light and essentially keep them trapped for relatively long periods of time. Then there's looking for direct detection of dark matter. Okay, so not direct detection, but direct evidence for dark matter coming from the gravitational lensing signature of two colliding galaxies, the so-called bullet cluster, where you actually see what happens is you have two galaxies. They pass through each other, they collide, but the dark matter clouds around them seem to be slightly displaced from the normal matter. As a result of this collision, you can see this effect through the gravitational lensing of the light behind the galaxies. And then also the advances in computation. So we'll talk about some of the lattice QCD calculations, but up to 10 to the 15th calculations of floating point operations per second and various applications. Okay, so let's talk about the early universe in the first stage. So this graphic is coming from National Geographic, produced by people, in particular the scientist here is Michael Turner from the University of Chicago. So in the beginning, you have the Big Bang, right? And in the very early stages, you have, so if you assume that at some point that there was some unification of the forces, we know the weak and the electromagnetic forces were unified. A lot of people believe that perhaps there's unification of the strong force as well as maybe even gravity. We don't know this for certain, but a lot of theorists think that this would be very elegant a way of describing what happens in the universe. But so at very high temperatures at the very early stages of the universe, so we're talking about 10 to the minus 43 seconds, sort of that short after the Big Bang, the forces were all of the same strength and of the same character, but then as the universe cools down, they behave much different from each other. Okay, that's here's suggested by the separations of these trajectories for gravity here, the strong interactions, the electroweak forces. Okay, and then also then a little bit later you have this period of what's believed to be rapid inflation. Inflation is the idea that the reason why the observed universe looks so homogeneous, you don't see big differences in different parts of the sky when you look with telescopes, is that there's this period of rapid inflation where space was expanding very quickly, and so that's why things became very uniform. You sort of diluted all of the matter that was in the universe, and so everywhere is pretty much the same. That's represented by these arrows here. Now then, after this inflationary period, you have all these hot matter. You have quarks and gluons and various things. And so this is the stage where you have these quark-gluon plasma. You have quarks that are not confined. They're so hot that they don't really care too much about confinement. But then what happens is, so this is something like 2 times 10 to the 12 kelvins. But then at some point, it cools down enough that the quarks do start to feel confinement, and they cool down, they stick together, form hadrons, baryons, and mesons. And so that's the quark to hadron phase transition. Okay, so something like about 10 microseconds after the Big Bang. And then after that, you have, once the hadrons are formed, the protons and neutrons and such, then you have the electron. Well, the electrons are already there, but then the electrons bind with the protons, and they form hydrogen atoms, and that's the next sort of phase that happens after that. Okay, so what do we know about quantum chromodynamics at high temperatures? So this information we get from lattice QCD simulations. And so here's some results, by the way. This is Alexei Bazarov, the first author on this paper. Alexei's in the physics department and the computational mathematical and sciences engineering department at Michigan State. And so this is simulations done by the Hot QCD collaboration. This other paper with Peter Petresky is also part of the same collaboration. So here's the temperature in megaelectron volts. Okay, and then we're plotting in one case the energy density divided by the temperature of the fourth power in kelvins, and then we have the temperature in megaelectron volts. And then we have 3 times the pressure divided by the temperature of the fourth power. If you go to very high temperatures, these things should be very similar to each other. They should approach the same behavior. And you also expect an approach to the Stefan-Boltzmann law that the energy density should be proportional to the temperature of the fourth power times Stefan-Boltzmann constant. Okay. Now, the actual behavior that you get if you measure the energy density divided by temperature to the fourth power, this is effectively measuring the number of degrees of freedom that you see. So you see at low temperatures, the quarks are confined, and the number of degrees of freedom are relatively small. Okay, so this is a dimensionless ratio, by the way. But then as you turn on as you increase the temperature, this is actually where the transition occurs. We believe there's a transition of critical temperature of about 185 or 195 megaelectron volts in temperature. Okay, and that's where you have a quark-gluon plasma as opposed to confined hadron gas. And so at that point, you have the quarks and gluons that can separate from each other because there's enough temperature. So they're hot enough so that they can move around. And so then you have an increase, you see a rapid increase in the number of degrees of freedom if you think of energy density over 2 to the fourth as a measure of the number of degrees of freedom. And then at some point it saturates out. Okay, you don't liberate more degrees of freedom and it flattens out and you approach the Stefan-Boltzmann limit. And these are, by the way, simulations done with different lattice QCD actions. So these are descriptions of how the simulations are done. You can also probe what's going on with quantum chromodynamics as a function of temperature by measuring the heavy quark anti-quark potential or strength, the coupling between the two. Okay, and this is on the horizontal axis is the separation between the quark and anti-quark pair. And if you're at cold temperatures, if you're below the critical temperature, so the critical temperature, remember, as just said, is about 185 or 190 megaelectron volts. If you're below the critical temperature, then what you see is that you have a rapid rise in the coupling. So this is confinement, if you like, as a function. So you see the energy is getting the coupling is getting stronger as you pull them apart. Pull the quark and antiquark apart, the heavy quark and antiquark apart. But then as you increase the temperature, you see these potentials or these couplings start to get weaker. At the critical temperature, you see it sort of flattens out. And then as you go to higher temperatures, it actually becomes weaker. So this is an example of sort of asymptotic freedom where the interaction has gotten weaker and you don't see confinement anymore at these high temperatures. Okay, so this, I mentioned asymptotic freedom. So this was the Nobel Prize of 2004, the work done by David Gross and Frank Wilczek at Princeton and David Politzer at Harvard. And so they looked at the behavior of quantum chromodynamics as a function of the energy scale or the momentum. And so they found that the coupling constant, we've talked about this before, it actually gets weaker as you go to higher temperatures. And here's a nice quote by David Gross at his Nobel lecture, that before we knew about quantum chromodynamics and this asymptotic freedom properties, we could not say much about the cosmology before 200 years after the Big Bang. We could only say things after 200,000 years. But after understanding QCD and the asymptotic freedom, we know that the physics actually becomes simpler. We can do calculations of the behavior of quantum chromodynamics at these higher temperatures, the early universe. So we can actually extrapolate back to the very early times when the nucleons have melted to form this quark-gluon plasma. Okay, so then you can ask the question, can you produce this quark-gluon plasma in theoretical calculations, maybe also in astrophysical environments, maybe with experiments? Okay, so in the Standard Model, the lattice QCD, lattice gauge theory calculations predict quantum chromodynamics deconfines, and you have this phase transition about, as I mentioned, somewhere around 190, 175 megaelectron volts. In cosmology, we believe this quark-hadron phase transition occurs in the early universe, going between quark-gluon plasma to hadronic matter. And in perhaps, this is not so clear, but perhaps also in astrophysical environments at the core of dense stars, you have some sort of quark-gluon plasma. I'm not so sure about this one. But the question is whether or not we can make this in a laboratory. So here's a little cartoon of of making a quark-gluon soup. Okay, and so by doing this, we can try to establish the properties of quantum chromodynamics at high temperature. Okay, how do we make a quark-gluon soup, plasma soup? So here's the temperature in log scale in kelvins. So we have 10 to the 15th kelvins up here for the quark-gluon plasma. And this is, if you like, the time after the Big Bang, how things cooled. So you have the Big Bang, you have then, you start off way up here, you're in the quark-gluon plasma region, and then you have hadronization where you form the protons and neutrons and pions. And then if you cool down further, you have nucleosynthesis where you form the actual nuclei, and then you have the atoms actually being formed after that. Okay. By the way, in this early universe, nucleosynthesis was really a very simple nuclei that you would form. You form the atoms, and then the stars will actually produce the heavier nuclei. And this is where we are now at the level of at the order of 1 Kelvin or so, and we're several billion years after the Big Bang. Okay, and then with accelerators, we can try at our time scale to reach higher temperatures to try to figure out what's going on with these quark-gluon plasmas. Okay, so just to review, the strong force, the nuclear force, it confines quarks and gluons to be in hadrons, but we can try to figure out what's going on with the quark-gluon plasma by compressing and heating these nuclei to melt the vacuum. So if we create an environment where we have a collision of heavy ions, we have lots of these nuclei, so we can get to higher densities and we can go to higher temperatures. Okay, so we start off by talking about the Heavy Ion Collider at Brookhaven since 2000, the year 2000. And so we have these various detectors that are measuring the properties of these collisions. So you accelerate the heavy ions to a speed of about 0.99995 times the speed of light. And so they use gold nuclei to collide these. So they collide gold nuclei, which have 197 protons plus neutrons are accelerated with these collisions. And if you want to know where RICT is located, it's on Long Island in Brookhaven, which is over here. And here is the star detector that measures these the results of these heavy ion collisions of gold nuclei. You have your magnets, you have your silicon convergence tracker that tries to reconstruct the trajectory of these particles that are coming out. You have your calorimeter that just measures the deposited energies, and you have your time projection chamber, and so on. And here's sort of to scale how big this thing really looks like. So a person would be about this tall, so you can see it's a pretty big experiment here. And okay, so you don't have to imagine people, this is the actual calibration being shown. All right, and here's the star detector. And I believe that's actually John Harris, the person who made these slides for the summer school. And here is a head-on collision for the vent, the gold-gold collision. So you can see there's just thousands of tracks that you can see here, and you have to have really good software to deal with all of this data coming out. That's the challenge of these heavy ion collisions. There's just tons of stuff coming out. Okay, now then, there's also been the Large Hadron Collider, so that's in Switzerland, in Geneva. And so the main, the main purpose of the Large Hadron Collider was to look at physics of the Higgs particle. That was the discovery, the main discovery of the Large Hadron Collider. But once you can make these accelerations of these hadrons, you can do lots of really interesting physics. So you can make them to do collisions of heavy ions, so in particular lead nuclei. And so here are 3 detectors that can measure heavy ion physics. So ATLAS and CMS, though, so there is an ATLAS group at Michigan State, which is mostly focusing on physics beyond the standard model, Higgs physics, stuff like that. And so that's not heavy ions, but they can measure heavy ion collisions. CMS is another collaboration similar to ATLAS, so they each have their big detectors that are special purpose detectors that can measure what they're looking for. ATLAS and CMS. Okay, now, and then there is ALICE, which is specialized for measuring the heavy ion collisions, as opposed to Higgs physics or beyond the standard model. And so here is, well, coming up in the next slide is a view of what's going on at the Large Hadron Collider from the movie Angels and Demons. You may have seen this movie. If you haven't, it's a fun movie to watch. And there's like 2 minutes or 3 minutes of footage from the Large Hadron Collider where they talking about injecting the heavy ions and various things to produce antimatter, the collisions. Okay, so this is from the movie itself. All right, so the LHC heavy ion program. So there's ATLAS and there's CMS and there's ALICE. Now they're doing lead-lead collisions. So the energy per nucleampere is 5.5 tera electron volts, and so they do the heavy ion collisions 1 month per year. So right now the LHC is off for upgrades, but they'll come back up with even heavier, with even higher energies. So from 2010 to 2011, they did lead-lead collisions at 2.76 tera electron volts, and in 2013 they did proton-lead collisions at 5.02 tera electron volts. By the way, if you're wondering what they do the rest of the year when they're operating, they're doing proton collisions for Higgs and beyond the standard model searches. So here is the ALICE experiment. So you can see it's similar in sort of style to the STAR detector. As you can see here, you have your beam line, you have your tracking chambers. Here's a zoom where you can zoom in of what's going on. Okay. And here are the lead tracks that you see from ALICE. This is an actual reconstruction of the data that they have produced. So I'll stop here, and we'll continue on with the lectures on the quark gluon plasma. We'll have 2 more lectures on this. Please email me if you have any questions, and send me a summary of today's lecture for attendance credit. So I'll see you guys on